All right, this is a tradition, if you've ever seen any of the revision seminars. Not that one. That one. For those of you who are watching online, I'm David. This is what I look like. If you've never met me before, hello. Right, that's enough of that. So this is my list of the techniques of integration that are covered in Mathematics 1A. I've listed them numbered them from 0 to 7 in order of how easy it is to actually do them. And the reason I've done this is because whenever you have a long or even a quite short list of different techniques to try in order to do something, you should probably put them in an order in order of how easy it is to achieve, and try them in that order. So it's much easier to just expand out some brackets than it is to do trig substitution, so that's the sort of thing you should try first. So whenever I do any integration problems, I start with my list and I run through the basic things on the left-hand side there that will normally produce an integral quite quickly, and then I'll start working through the things that are designed for specific crazy cases, which are on the right-hand side. Unless, of course, I've specifically asked to use a specific method. But traditionally, in the exams over the last few years, there's usually a question that goes, you know, here are some integrals, do them, and it won't tell you how. So it's useful to have a list to choose from. Not that you can take this list with you, but you can in your head. That's why I show this to you. And you'll note that trig substitution, it's like number 5 on this list. It's quite a long way down the list. And I've very carefully lined these up. The basic methods are just doing it, because you just know what to do. Rewriting it, which is expanding or simplifying or using a trig identity. Substitution and integration by parts. And then on the other side, reduction formula is next to by parts because traditionally you use by parts to do it. So it's sort of a very fancy version of by parts. And trig substitution is next to substitution because it's a very fancy kind of substitution. And partial fractions is just a very fancy way of rewriting it, and doing it numerically is giving up and not doing it at all. Well, it had to go somewhere. So it's nice that it's at the top because sometimes it's the only thing you can do, and so you just start there. There you go, that's the quick intro. Now I can actually talk about trig substitution. So if we zoom in on this, it says that trig substitution is for powers and roots of Pythagoras-ish expressions. And there are 3 pieces of advice to go with that. Use a trig identity to decide which one to do. Work the substitution to put it in, and work the substitution to get x back, and I'll tell you what I mean by work the substitution as I do the examples. So the key is that these ones on the right-hand side are for specific kinds of things, and there's flags in the function that you're trying to integrate that tell you that it seems like an idea to do it. Can I turn that off at all? Okay. And the thing that seems like the right idea, that tells you that trig substitution seems like the right idea, is that there's a Pythagoras-ish sort of expression, meaning it's something plus something or minus something squared. Okay, the sort of thing that would happen if you attempted to figure out one side of a right-angled triangle upon knowing 2 of the others. That is what we're looking for. Right, I'm going to start with an example. Be aware that I usually make these things up on the spot, so bear with me if I do something a bit dodgy. Okay, so I'm just going to do some examples. Let's start with this one. Let's start with this example here. And I'm going to do exactly what I do for all integrals and work my way down the list, just in case trig substitution is not the thing I'm supposed to do. So the first thing on the list is to say, can I just do it? No, well, it's not something that's on my standard list of derivatives that I happen to recognise. But it's not far from that. Like if this was just 1 minus x squared without the 4 there, that would be the derivative of arc sine x, which is one of the derivatives you're supposed to just know in Maths 1A. And so that reminds me of something that I'm used to, and so I can move on to the next stage, which is rewriting it in another format. So I could go like this. Because the 4 is 2 squared, so I can bring it inside the square like that, and it will get square rooted along the way. And now this is exactly what I would have if I differentiated arc sine of 2x, except it's missing the bit that normally happens when you do the chain rule. And so I can just do it by doing what I would normally do if that was an x, but it's a 2x, so I'm going to have to divide by that constant. So while it may look like it's the sort of thing that trig substitution works for, something that's sort of Pythagoras-y, it's got something and something squared and a root, I don't need trig substitution for it. I can just do it. Sorry guys. So this question. Some lecturers have a tendency to put a dx on the top of a fraction if there's a 1 there. It's one of the things they do. Technically, what we're doing here is that the integral sign here is just a thing that happens to this thing. So you can either view it as that these two things work together like brackets to tell you what to do to that, or you can think of it as that this combines with the dx and then we add them all up and it produces the answer. So thinking of it that way allows me to see the dx as a thing that multiplies. Anyway, it's not... I'm putting this here for a reason. It's not quite Pythagoras-y. And normally a Pythagoras-y thing would just be, you know, a constant, like something squared and one other thing, but I've got 3 pieces here. But it is something squared. And anything that has a square in it and lower powers can be rewritten as something squared plus or minus something else. So I know that I can rewrite it in a format that works. I mean, I should check, no, can't just do it. If I did u equals the, and then a substitution, if I did u equals the bottom, I'm going to need to add 2x plus 4 floating around there, and it's just not there. So I can't do the things on the list that I've already covered. I'm going to have to try something else. And rewriting it is not the worst thing. And in fact, it's earlier on the list. Sorry. I'm going to complete the square. Okay. So this thing, I'm going to want to rewrite. Might take me a few lines to do. So that it's like something squared, maybe plus, maybe minus something else. So something's going to go in this space here, something's going to go in this space here. And when you complete the square, you sort of imagine that if this was x plus something squared, when I expand it out, I get x plus 2 something x, x squared plus 2 something x plus something squared. And so this thing here must be 2 times the something, which means I divide that by 2. X plus 2 squared. course, if I expanded out x plus 2 squared, it would totally be x squared plus 4x plus 4. I'm filling in from the top and the bottom. So, well, I don't have a plus 4 up here. So what I'm going to do is I'm just going to do this. Is put a bit of space and put one in and take one away. One of my past staff calls this a Cinderella moment. It's like, Cinderella says, oh, I'd like a plus 4, and the fairy godmother says, here you have, bippity boppity boo, but you have to give it back at midnight, which is this bit here. I know. Okay. So this bit here I'm going to keep the same because it's going to turn into the x plus 2 squared, and this bit's a 9, and so ta-da. Probably a few more lines than I would normally use, but that's the idea behind it. So now it's good, I've turned it into this. So I've left the integral sign off because I'm going to do a little bit more work in a second. So now I'm going to look at that and start it as if it was a fresh integral that I'd never seen before. And so I'm looking at it, it's sort of Pythagoras-y. It's got a squared plus another thing. But even before I get to that, I should look to see if it maybe should be something else. Maybe I should just rewrite it if I'm really careful. Let me just think. 1 over x squared plus 1 would be the derivative of arctan x. So that's not too far from that. It's just got that 9 in the wrong spot. Well, and the x plus 2, but we can deal with that another time. So if I maybe divided the top and the bottom by 9, I get like a 9th over x plus 2 squared on 9 plus 1. You cannot read that at all, sorry. Like that. It's looking pretty good. Arctan's got a 1 on the top, so I'm just going to put that over there. And arctan doesn't have a thing here, so I'm just going to bring that 9 inside the square, and it'll become a 3. Sweet, I can do this. I can totally do this. Because now, if that was just x, it's arctan when I integrate it. And it's not an x, but the derivative of what's there is a constant, so all I need to do is divide by that constant. Yes! You'll note I haven't even got to trig substitution yet, but that's the point. So let's see, when we integrate things, the 9th will stay there because there's a constant multiplied on. All of this would become arctan, only it's not an x and it's an x plus 3, plus 2, sorry, on 3. And since the derivative of that is a constant, I can just divide by it, so I just divide by a third, which is the derivative of that. Beautiful. Just guess maybe combine all those numbers. Dividing by a third is the same as timesing by 3. 3/9 would be a third. I should say that some people, when they do this integral, know off the top of their head how to go from here direct to there. They have a formula that they just remember. Your engineering lecturers and your physics lecturers are very commonly going to do that sort of thing. They're going to go, oh, I know that one. It's just like 1 over root that number over x plus 2 over root that number. That's just how they're going to do it. So if you are blessed with a memory that is better than mine, go for it. I have a feeling that your maths lecturer would prefer you to do a little more working than that. But your physics lecturers will be sweet with you going direct from here to here with the integral. Okay. The point I'm trying to make there is that you can do these things without doing trig substitution sometimes. Because in a way, trig substitution's fancy, and I didn't really do anything very fancy. When you look closely, I just, in inverted commas, move some of the numbers around into different places. Now, for some people, moving some of the numbers around when there's fractions within fractions is just asking for trouble. And I'm one of those people most of the time. So know yourself about what is going to be likely to cause upside down errors and minus sign errors. But still, I think this is kind of nice that you can do it without. And in the past several years of exams, there's totally been one very like this. Normally it comes under partial fractions, but technically we didn't use partial fractions. So if you look in the book, in your book, in the notes. All right, now I'm really up to trig substitution. I warn you now that I am. Let's have a look at this one. Aha. Well, let's see. Doesn't look like something I can just do. If I did ordinary substitution, I could maybe call this bit u, and then the derivative of that would be like minus 2x. And I do have an x here, so that'll be part of the derivative, but then there's an x left over, and so it's going to turn to crap. It's not going to work because I have got the derivative of this, but I've got too much. Sometimes that's okay, but the too much is going to have a root in it again, and it's not going to serve the purpose of getting rid of the root. The whole purpose was making the root go away. So I think that ordinary substitution isn't going to work. I suppose if I was very clever, I could rewrite it, maybe like minus a 48 on the top, and I'm just still going to have a root in it no matter what I do. So I reckon trig substitution's the go. Trig substitution is specifically there to help get rid of roots. That's what it's for. So let me just go back to the screen. My advice was, bang, use trig identity to decide which one to do. Now, most people blessed with a memory better than mine will look at the format that this is in and go, oh, well, that's obviously x equals a insert trig something insert trig function x, u or something. They'll just look at it and know what to do because they have a list in their head of which shape of triggy thing, of Pythagoras thing, goes with which trig substitution. I personally cannot do that. I'm no good at remembering these things, and I only do trig substitution twice a year. Once in Maths 1A in semester 1 and once in Maths 1A in semester 2. And so it's not worth my pain. And so I find a different way of dealing with this that doesn't require me to remember anything new. And it's to do with trig identities. Now, trig identities themselves, I have a way of dealing with that doesn't require me to remember anything new either. I know one trig identity. Well, I know several trig identities. One trig identity that involves squares and a couple of others which are the double angle formulas. So I know it's going to be one of the trig identities that involves squares because look at all the squares. It's 16 and an x squared. So let's run with that. Let's see. Does your lecturer use theta? I apologise. I can only use u's when doing substitution. I can use theta, but my thetas look stupid, so. They mainly just look like O's, which look like zeros, which doesn't help. So this is the fundamental trig identity. I can remember this. And what I need to do is try and turn it into a trig identity that matches what I've got there. So what I have there is I have a constant minus a variable squared. Constant and variable. And currently it's variable and variable equals constant, but if I rearranged it just a little bit, then it's looking the right shape. Constant, constant, minus variable, variable. It's looking right. It's matching much more closely to what I have there. Only problem is the constant is a 1, and this constant is a 16. So I'm just going to times everything by 16. Like that. That's looking good. I've got 16 minus... this is supposed to be just a single thing squared, so I'm just going to bring that 16 inside the squared. It's looking good. And so, cool. Look, if this thing in here was x, it'd match exactly. So that's what I'm going to do. So let x be 4 sine u, so that this thing is now 16 minus x squared. And it matches precisely what is in my integral. But the thing in my integral has actually got a root, so I'm just going to do the square root of both sides. So like that. I suppose technically when I do a square root, there's supposed to be a plus or minus. But if I'm really careful about u, I can just arrange it so that the cos u is positive anyway. Where's cos positive? Cos is positive over here, isn't it? Beautiful. If cos is over this side, if the u is over this side in those quadrants, then cos u is going to be positive. Which means that when we do the square root, we don't have to worry about the plus or minus. Sweet. Also conveniently covers all the possible values of sine u. Which is really cool. The place where the domain of arc sine is the place where cos is positive, and the domain of arc cos is the place where sine is positive. It's pretty cool. One of the reasons they were chosen the way they were. Okay, so what have we done? Just a second, just a cotton pick a minute. So we've just dealt with this. We know what this is in terms of u. It's 4 cos u. Okay. So we've still got to turn everything else into u. I'm going to deal with the dx next. Normally when you do substitution you deal with the dx first, but it was easier for me to deal with the bit in the root first. So let's see. So we knew that x was 4 sine u, and so dx on du is 4 cos u, and so dx is 4 cos u du. Okay, so back in my integral. Oh, that's bad, sorry. All right, I've dealt with the dx. I can replace that with 4 cos u du. And that just leaves me to deal with this 3x squared. Oh, well, I can do that too. X squared must be 16 sine u squared. So we want 3x squared, don't we? 3x squared must be 3 times 16. 3 times 10 is 30, 3 times 6 is 18, 48. Okay, so let's just go back. We've got a 3x squared. Excellent. I've covered everything. I can replace it all. So the integral of 3x squared over root 16 minus x squared dx is now, so 3x squared was 48 sin u squared, and the dx was 4 cos u du, and the root 16 minus x squared was 4 cos u. So everything's now been replaced with something involving u. And now I pretend this is a brand new integral that didn't come from anywhere, and just try and solve it the way I would solve any integral. So let's see. Well, I think doing some simplifying couldn't hurt. They have conveniently cancel. And we have now done part 1 of the trig substitution. One of the problems with trig substitution is that it takes a long time. But, you know, what is it I say? Possible is easier than impossible. So we have turned an integral that we couldn't do into an integral that we can do. And yes, we can. Okay, so now we're going to pretend this is a brand new integral and go back to the beginning. Can I just do it? Well, if it was just 48 sin u, I could do that. I can integrate sine, but it's a sin u all squared. I could try and do a substitution. If I went like v equals sin u, yeah, but the derivative of sine would have to be there, and it's not, so it's not substitution. By parts, maybe I could do by parts, because I could write the sin u as sin u times sin u. Yeah, but I reckon when we integrate one, differentiate the other, we're going to get cos squared, and we don't know how to do that either. Okay, so just a second. I should have gone right back to the beginning. Maybe I could rewrite sin u as something else. Oh, of course. Just a second. Sin u squared is in a trig identity. We already covered that. But these trig identities is only going to turn it into a cos u squared, which I also don't know how to deal with. So I need a different trig identity that's got sin u in it, squared. Cos 2u is cos u squared minus sin u squared, which is you know how I said I only know like 3 trig identities? I don't know this one off the top of my head, but I can get it from this one by replacing the cos squared with 1 minus sin squared. Okay, and I can rearrange this. So if I put this over there and this over there, so technically adding 2 sin squared over this side and subtracting cos 2u over this side. And what do we need? We need 48 sin squared. If you times by 24, that'll do the trick. Brilliant. Okay, so my integral is now this. Brilliant. Okay, that's part 2. So part 1 was turning my original integral into something involving trig. Part 2 was turning that trig integral into something I actually know how to do. Part 3 is actually doing this integral, which I can do. So the integral of 24 would be 24u. This one here, that 24 is multiplied on, so it'll still be there. And that 2u there is just a constant times u, so I can just pretend that it's u. The integral of cos is plus sine and I'll have to divide by that constant there. Doing so well. So we have 24u minus 12 sine 2u. Brilliant. Okay, so what have we done so far? We've turned our original integral into something involving u, which was trig. We've now figured out what the integral of that is in terms of u, but my original integral has an x in it, so I'm going to have to put it back in terms of x. Okay. We can do it. Yeah?
Before you switch, on the third line of the page, how did you get from cos u squared take sine u squared to 1 take 2 sine u squared?
This one?
Yeah.
What I did was I noticed that this thing here was 1 minus sine u squared. And I subbed that in. And so I end up with 1 minus sine u squared minus another sine u squared, which just gives me that. I'm extremely happy that you were brave enough to ask this question. It's important to ask these sorts of questions. If you can't ask that question of a Maths Learning Centre lecturer, then who can you ask? Okay. Yeah, the reason I can't do... I mean, some people can remember this one straight up, but I can only remember this one. And the reason I can remember that one is because the other one's cos squared plus sine squared, which is 1, and this one's cos squared minus sine squared. So because they're similar, I can remember them both. Interestingly, cos squared minus sine squared is 1. And cos squared plus sine squared is cos 2u. They're the other way round. Gotta love the hyperbolic trig functions. Okay. Right. So I need to put my u's back. All right, let me go back to what I said on the screen. I said we should use a trig identity to decide which one, which is what I did. I went, oh, I'll just find the right trig identity that matches my thing under the root most closely, and that's how I'll decide which substitution to do. I did that. Tick. I worked the substitution to put it back in. What I mean by working the substitution is all of those calculations I did by looking at each piece in terms of x and figuring out what it was in terms of u, and doing all that calculation before I subbed it all in. Because if you do it inside the integral, you have to write integral signs all down the page, and it just looks messy. The last thing we have to do is work the substitution again to get the x back. So we need to go back to our original statements about what u and x are and do some algebra so that we can figure out how to put them back. Okay. So what have we got? We've got a u. All right, well, we know that x is 4 sine u, so we can rearrange that to get what u is. Okay. So x on 4 is the same as sine u, and so arc sine x on 4 is u. Now let's just check that we've done all this right. U is a result of doing arc sine on something, so it must be between minus pi on 2 and plus pi on 2, which it is. Isn't that convenient? That's the reason why we choose them this way, so that everything all works out the way it's supposed to. Okay, so I've figured out what the u is. I won't do big circles and ticks this time, I will just underline them. Good, I've got the u. All right. I need to just sine 2u. I don't have any sine 2u's. So I'm going to have to make it myself. Okay, so sine 2u would be 2 sine u cos u. That's the other trig identity that I know. Well, actually, I know a couple more, but only if I'm pushed. Okay, cool. Now, just a second. We do know what sine u is, because sine u is x on 4. We just wrote that down. We just need to figure out what cos u is. Oh look, we have cos u. 4 cos u is equal to this. So I can figure out what cos u is. It's there. Okay, cool. Sin u is x on 4. We just wrote that down. And cos u... 16 minus x. So actually awesome if I just times them together. No, it's not going to work. So, oh, thank you. I'd love a little laser line that showed me where I was. You can't have everything. I have like the most awesome job in the world. I can't really complain about not having a laser line that tells me where I am. So my sine 2u, which is sine 2 sine u cos u, sine u is x on 4, cos u is this, and that's going to come out to whatever it comes out to. I suppose technically I actually have 12 of those. I could figure that out. So let's see, that 4 can cancel with that to make a 3. That can cancel with that to make a 2. So it looks like we get 3 on 2x root 16 minus x squared. Now where were we? Back here. We figured out what the u was. We figured out what this 12 sine 2u is. So my integral is now this. The 24 and the u was arc sine x on 4, and the 12 sine 2u was this. And we're done. If I had, 20 minutes to spare in my exam, I'd differentiate it and see if I got to the original answer. Or not. But failing doing that, yep.
I was just wondering, in that first trick, like cos u squared plus sin u squared equals 1, you made everything in terms of sin u.
Yep.
Could you do it the other way with cos?
This is a very good question, which I'll repeat for the recording. At this point here, I moved it so it said 1 minus sin u, and so the sin u end up being the x, and you're saying, could you have done it the other way around and put the cos u there? Yes, I could. I could totally have done that. There's a good reason why I did sine, and that's because when I differentiate the sine, I won't get a minus. And I know, knowing myself, that the more minuses there are, the better chance I have of losing some of them. Because if I lose 2 of them, then it'll be okay, but really don't want to go there. Don't want to trust my ability to lose an even number of minus signs. Yes. So let's just go back and make sure we've got all this in the right order. Right. So we have our original. Let's see what we did here. I made some decision. Some people can look at this and go straight to here. But then in order to use that, they're going to have to do this working anyway, just in a slightly different order. Okay, so the reason I have chosen to do it this way is that I have to do that working anyway, so I might as well use that working to help me make the decision. It's more efficient. But you do whatever works for you. If you don't have something that works yet, then maybe this. And then I dealt with each piece that was left and figured out what it was in terms of u, including the dx. And then, after I'd done that, I had to use more trig identities to do this. Sometimes, if you're really lucky, it'll just come out to a whole number. It'll be like 48. There won't be a sine squared, and you can just do it. Okay. Sometimes, if you're lucky with what you come up with today, or with the mind of your lecturer when they wrote the exam, you will find that you can just do this without having to do all this trig identity stuff. But in an exam, it's usual for someone to expect you to test more than one aspect of the course at a time, and you were taught about doing trig integrals, and so using it as part of your trig substitution is efficient in the mind of your lecturer. So, yes. And then we did the integral, and then we had to do more work to figure out what each piece of that was and put the x back in. The reason I say all of that is so that you can keep in your head a list of things to do. One of the things that makes a long process easier to cope with is to have pieces that it's made of. So having a list of things to do in your head of figure out the substitution, deal with all the x's, do some trig identities to do that integral, deal with all the u's, that's 4 things to do and it doesn't seem so bad as one huge thing. So there's my advice. Alright, I could stop there, or I could do another one. Maybe just up to the point where we sub it in, or not. I'm going to let you guys tell me what you would prefer. Do you want me to stop there, or do you want me to do another trig substitution? Another one? Okay. More, again! Does anyone have a particular example in mind? Because otherwise I'll just make one up. Right, I am going to choose one which has another nuance that we're going to have to possibly deal with. Oh man. Use 16 too often. Well, let's have a look at that. I could rewrite it. Well, I mean, that's how I normally expand it out if I wanted to do that. Yeah, that's not going to happen with a 3 on 2 there. That's a 3, by the way. The next thing on the list is substitution. So if I go u equals a bit in the middle, the derivative of that is sort of x-ish. Oh, and I've got an x. Oh, even better. Okay. U... So if I differentiate that, I get minus 10x. Now what have we got in x dx? So I'll just put that over there. And so this is going to be, so the x dx is going to be minus 1/10 of du, and this bit is u. And I can just put the power up by 1 and divide by the new power. That'll go up to 5 halves. So what's that? Minus 1 on 25, u to the 5 on 2 plus c. And I can sub it back in. I will do a real trig substitution in a second. Just wanted to make a point. Okay, just because trig substitution is what is in your mind at the moment doesn't mean that it's what you'll have to do. Always check to see if it's an ordinary substitution first. Okay. Let's give this one a go. I have no guarantee it's going to come out to anything good. Okay? When people write your exams, they have like several weeks to do it, and someone checks it. So, yeah, better off than this. Okay. So I need to do something. Let's just check. Ordinary substitution. Well, can I expand that out? No, roots don't do that. They don't expand out over minus. Can I do ordinary substitution? No. I need the derivative. I need an x on the outside, which I don't have. Could do it by parts. Could put a 1 there, and then if I sort of integrated the 1, if I just get an x squared on the top, it's not going to happen. I reckon Trig substitution really is the go. So let's see. That's my fundamental trig identity. So I need variable squared minus number. I suppose I could get that, right? I could do like, I could put the minus 1 over here and the cos over there, but then that'd be like sine squared minus 1 equals minus cos squared, and I'm never going to be able to do the square root of a negative. Okay, so I'm going to have to do something else. What's that other trig identity? If I divide it by cos squared, I'll get this. So cos squared divided by cos squared is 1. Sine squared divided by cos squared is tan squared, because cos over sine over cos is tan. And 1 divided by cos squared is sec squared, because sec is 1 over cos. That's the other trig identity. And you'll notice that this one has a decent thing. It has number plus variable squared. So if there was a plus here, I'd be good. It's a minus though. So what I'm going to do is I'm going to rewrite it like this. So I do have to have a little bit of knowledge. I do have to know that there is a trig identity that does have a plus, and it's got a tan and a sec in it. So I know that I do have to know in advance that sometimes I have to divide by cos squared to get what I want. But for me, that's somehow easier than remembering any of the other things. So there we go. That's looking the right shape. This is looking right, except what have we got? Something squared minus number, something squared minus number, but the number's supposed to be 5. Okay, so we're doing well, but this has to be written as something squared. It's looking pretty good now. If this was x, it would match. X squared minus 5, x squared minus 5. Brilliant. Okay. So let's just deal with that thing there. So that means that now, so 5 tan u squared is now x squared minus 5. And so when I do the root, I'm going to get root 5. Okay, so we're going to need to arrange for tan to be positive. Tan's positive there, so I'm going to need to say that for u is in, man, how do I do that? Minus pi on 2 to minus pi. Oh, that's the wrong order. And from 0 to pi on 2. Excellent. Oh, crap, it's not going to work at the ends. They have to be round brackets. Bang! Okay, that's going to make my tan positive, and it does conveniently cover all the values of sec, because sec is cos, basically, so which cos is positive up here and negative down here, so together we've covered all of them. Brilliant! So let's see. We've dealt with this, that's good. That just leaves the dx. Brilliant. Dx on du be root 5 sec u tan u. This is one of the derivatives that the people who write Maths 1A exams expect you to know, and it's kind of cute. It's one of my favourites. I like that the derivative of sec and the derivative of tan both involve sec. Okay. All right. So let's see what we've got. So my root x squared minus 5 becomes root 5 tan u. My dx becomes root 5 sec u tan u du. I really should have written that in, shouldn't I? It is okay to go straight to that, straight to here if you like. Some lecturers do that as well. Okay, so what have we got? So the root 5s will become a 5. We've got a sec u, and we've got, that does not look like a sec, it looks like a su, and a tan u squared. Man, this is supposed to be easier. It's okay. Possible is better than impossible. Right, let's go right back to the beginning. Can I just do it? Well, I would have done it by now. What's the next thing on the list? Rewriting it. I could possibly use some kind of trig identity. If I did the tan squared could be replaced with sec squared minus 1 from the previous page. But that would give me like a sec cubed and a sec, which I don't know how to do. Okay. Yep, I think we're into one of those situations where it turns into sec. Sadly. Which tells me that what I probably should have done is a hyperbolic trig substitution, which I could show you, and that would be awesome fun. But I don't really know if it's in your exam or not. Not that I know whatever's in your exam, I didn't write it, they don't show it to me. The first I know of your exam is when the exam solutions the next semester come out and people ask me about them. Unless you're all very nice and you come and lick your wounds in the Maths Learning Centre after the exam. It looks like my only choice is to turn it into something sec-ish. Yeah, I could try a substitution. There's no point doing like v equals sec u because I just came from there. I could do tan u. But I have a feeling that's not going to help because I need a sec squared and I haven't got a sec squared. No. By parts might work. Because like I know how to differentiate tan squared using the chain rule, but I can't integrate sec though.
Can you turn it to one more?
I can integrate sec u. I can integrate sec u tan u, that'll become a sec, the tan will become a sec squared. I'm going to get a sec cubed anyway. All right, sec cubed is what we need to integrate. Do you want me to do that? It's not going to be fun. Yeah. I can try. We can do it. Just a second. I know what we have to do. Sec u plus tan u. Well, that's what we have to do. Well, man. There's some sort of reduction formula, I'm sure. I'm going to try integration by parts. That's what integration by parts looks like. Except it's got some dashes in there, but I'll deal with that in a minute. And I need to integrate one of those things and differentiate the other. If this one had the dash, I'd have to integrate it, and I don't know how to integrate sec. So I'll put the dash on that one. Okay. So what we've got is we've got f is 5 sec u, and g dashed is sec u squared minus 1. The integral of that is tan u minus u, and the derivative of that is 5 sec u tan u. And so what we get is f, which is 5 sec u, g, which is tan u minus u, minus f dashed, which is 5 sec u tan u, and g, which is worlds worse, because now we have a sec u tan u u. Though to be fair, I can integrate sec tan and I can differentiate u. It's still going to give me the integral of sec. Yeah, there's an answer for that. So I'm going to cop out. Yeah. Wouldn't you need a sign on the top? I suppose that'd be a sine squared and a cos cubed. Yeah, I'm going to say write that on the exam and it'll give the marker a thrill. You won't get the marks, but okay, I should say it is possible to integrate sec u, and therefore conceivably possible to integrate sec cubed u by parts usually, because the sec squared can go up to tan, and the sec can go down to sec u tan u, and you'll end up with what you had to start with. And so you'll have to do the whole little trick where you get what you start with and you put it back at the beginning and you divide by 2 and that sort of thing. So it is possible, but not today. That is enough of trig substitution for now. What I wanted out of that question there, what I wanted hopefully us to learn is how to tell if it's a sec that you need to substitute. And that was involving a trig identity that involves sec, because that's the only one that has a reasonable version of variable squared minus 1. Who taught you calculus this semester? Was it Nick Bookdale? I'm pretty sure he won't do it in his exam, but Nick Bookdale is known to love hyperbolic trig substitution. So it is not impossible that he would give you something like this and tell you to do a hyperbolic trig substitution. But it may not be worth your effort learning to do that right now. Meh, here we go. I'm going to do it. Just to show you something. My trig identities got me to can be done but not today. Alright, that's where it got me. What if I did a hyperbolic trig identity? My ordinary trig identity, which starts out like this, got me to things I couldn't do. So maybe, if I do a hyperbolic trig identity, it'll work. The ordinary one has a plus in this spot, and the hyperbolic one has a minus in this spot. I always write my trig functions in alphabetical order so that I get the minus in the right position. It's cosh squared minus sine squared, and the cosh and the sine are in alphabetical order, because it's not sine squared minus cosh squared. This is not too bad. I have variable minus variable squared. I need variable minus number squared. If I put this number over there and that variable over there, it will be that. And that, my friends, matches. The cosh squared matches with the x squared. The 1 is a number. I just need to multiply everything by 5 so the numbers match. Like that. And then I need to make sure this is a single thing squared, because that's what it is there. Which is great. Let that be root 5 cosh u. Then we get x squared minus 5 is 5 sine u squared, which means that x squared minus 5 is root 5 sine u. Now, sine has to be positive, which means the u has to be positive. Sine is positive when the thing inside it is positive, and negative when the thing inside it is negative. So that means that back here I need u to be greater than or equal to 0. Because sine, the graph of sine looks like this. Like that. Conveniently, the graph of cosh looks like this. And cosh isn't invertible. I'm going to need to choose half of cosh if I want to be able to undo this cosh over here, which is nice because the u is greater than 0 does the trick. I have to say I'm most impressed with myself for doing this whole basing it on the answer that you're supposed to get, because I've never done that before today and it's working out so well. Okay, so we've dealt with this bit. We just need to deal with this bit. We just need to deal with the dx. So dx on du will be root 5 sine u. Like that. And I just times by the du. Now just let me check. The derivative of cosh is plus sine. When you differentiate them, the minuses don't happen at all with this, with the hyperbolic ones. Okay. And so we get the integral of root x squared minus 5 dx is now, that bit was root 5 sine u. The dx is root 5 sine u du. And that's coming out to 5 sine. Brilliant! We just did one that was sine squared, so it should conceivably be possible to do one that's sine squared. I just need the double angle formula for cosh and sine. Okay. It's exactly the same as the double angle formula for cos, only with a plus. Pretty sure. E to the 2x. Yes, okay. Those of you who are listening to this didn't see me standing there staring into the air waving my hands while I was doing the carrying of the 2's. Okay. And so I can rearrange this. This would be the same as, now just a minute, cosh is 1 plus sine u squared. I'm just going to do that straight up. So if I just write them next to each other and do this and sort of do this minus this, I'm going to get cosh 2u minus 1. That minus that is 0, that minus is 2. Yes! And so I need a 5 here, so I'll divide everything by 2. And times everything by 5. Brilliant. It's now become this. So the 5 on 2 will stay there. The integral of cosh is sine. And I have to divide by the 2. Sorry. 5 on 2 stays there because it's times on. The integral of cosh is sine. The 2u is still there, but because there's a constant there, I have to divide by it. And the 5 on 2 will go up to 5 on 2u. And now I have to do that last bit of putting everything back. Oh, man. So it seems reasonable that I should expand that out. So what happened there is that these 2's went together to become this 4, and the sine 2u becomes 2 sine u cos u. That's the same trig identity as the ordinary trig identity. Right, so just a second, what have we done so far? We've figured out what substitution to do. We've done some trig identity things to sub it in. We've done the trig identity to do the... Sorry, I was just trying to think about how to do trig identity with an H in it. Thrig. Anyway, sorry. And we've done the integral, and now we need to put it back in. I know what u is because I can rearrange that from here. I know what cosh u is because I can rearrange that, and I know what sine u is because I can rearrange that. So from before, we had that root x squared minus 5 is root 5 sine u, which means that sine u is root x squared minus 5 on root 5. We also have that x is root 5 cosh u, which means that cosh u is x on root 5. Sorry, guys. And that also means that divide by the root 5 and that means that a cosh x on root 5 is u. And so finally, we can sub it all back in. What have we got? 5 on 2 sine u, which is root x squared minus 5 on root 5, cos u, which is x on root 5, minus 5 on 2 a cosh